Everyone knows AI started in the 1950s. Everyone is wrong by about 2,000 years. You talk to math every day. When you ask ChatGPT a question, you're conversing with statistics, lists of numbers connected to words stored in a vast multidimensional digital space controlled by computer chips. In the future, we're going to have to explain Google.com to our kids. And when we're done explaining it to them, they're going to say to us, "You mean you had a question and a machine just gave you a long list of websites and you had to click through them one by one, dodging all these ads and junk just to piece together maybe an answer?" That sounds super broken. The scale that we use AI tools today would have sounded impossible or absurd just a few short years back, yet we've already normalized it. Like we normalize every impossible thing, then promptly forget it was ever impossible. In conversations with academics and clients and other people that I've had around me, I've noticed something that led me to talk about this specifically and why I started to say that everyone's wrong about AI by about 2,000 years. Most believe that artificial intelligence emerged with Alan Turing, or perhaps some of the original numeral integrator computers in the 1950s. Some really just think about ChatGPT and Claude, and they're particularly disconnected from history. Not everyone, but a good portion don't understand that there were steam-powered pigeons in ancient Alexandria. There was medieval Arabic robots that could be reprogrammed daily. They're unaware that Victorian looms were wove from patterns of punch cards that were literally the first stored programs, decades before anyone even imagined electronic computers. And even if they do know of some of this history, some of the factoids, they forget to connect it to today's modern AI hubbub. This amnesia, this forgetfulness matters when we think of AI as 70 years old rather than 2,000 years old. We miss an important pattern, and patterns are everything. We fail to see that every generation has built thinking machines of their own, each time believing they'd either achieved the impossible or hit the absolute limit of what machines could do, the edge of abstraction. Yet we always found a way to abstract further. You see, the first programmers used sticks and stones. Literally, in Alexandria around 62 CE, we know the date because Heron references a lunar eclipse visible from Alexandria on March 13th of that year. An inventor built what we now recognize as the world's first programmable robot. Heron of Alexandria's automatic theater wasn't just a clever mechanics, it was programmed entertainment. A 10-minute performance of Dionysian myths unfolded through acts of movement, fire, liquid pouring, and dancing figures. The programming language was rope, knots, and falling weights. Binary-like systems of wrapped and unwrapped cord around rotating drums determined which actions triggered when. A millet seed timer, right? A bunch of small little millet seeds controlled the tempo. Sand would have been too fast, water too unreliable, especially in the Egyptian heat. Think about what this means. Before Rome fell, before the Dark Ages, before the Renaissance, someone had already solved the fundamental problem of programmable automation. Heron didn't just make machines that could move, he made machines that could follow instructions, that could be reprogrammed by changing the arrangement of knots and pegs. The syntax was mechanical rather than digital, but the logic was identical to what runs your smartphone today. If this condition, then that action. Yet Heron's theater was primitive compared to what the Greek mechanics had actually achieved 2 centuries earlier. Yeah, you thought I was moving forward in time? No, we get to go even farther back. 67 CE isn't even close to the earliest. The Antikythera Mechanism, pulled from a shipwreck in 1900, was dated to around 100 to 150 BCE. Computed astronomical positions with shocking sophistication. It wasn't just simple gears. Any clock has gears. This was gearing that allowed other gears to mount to others and created complex motion from simple rotations. The device calculated ecliptic longitudes for the moon, the sun, and all 5 visible planets. It predicted eclipses using 18.2-year Saros cycle. It even accounted for the moon's elliptical orbit. A mathematical subtlety that wouldn't be formally described until Kepler 17 centuries later. That's 1,700 years later. The mechanism employed differential gearing, a technology we credit the Industrial Revolution for. When researchers finally decoded its full function around in 2021, they concluded it was a mechanized the predictions of scientific theories and could, realistically, have automated many of the calculations needed for its own design. In other words, the ancient Greeks built a computer that could have helped design itself. Maybe I'm taking it a bit far there, but the idea is the same. All of this context is saying helped design itself. It's almost like saying the brain designed itself. So perspective becomes important. Now, let's move forward a whole bunch here. The memory machines of Baghdad. This is when mechanical knowledge reemerged. It went through a little bit of a dark period there. And it actually came from Baghdad in the Middle East, not Athens. In 850 CE, the Banu Musa brothers described something extraordinary in their book of ingenious devices. It was a flute player that could be programmed by its user. Steam powered the mechanism, but the user controlled which melodies emerged. Different configurations produced different songs. Now, the goal was not a simple automation trick. It was a user programmable automation, the conceptual leap from machine that does one thing to machine that does what you tell it. A very important nuance to note, pun intended, as we move forward. Making songs is interesting, but a production line of machines is needed to really start making progress. And this is where Al-Jazari, chief engineer to the Arctwid dynasty, comes into play. In 1206, the year he died, he completed a manuscript describing 50 mechanical devices. His castle clock, standing 11 feet tall, did more than tell time. It could be programmed daily to account for the changing length of days and nights through the year. The clock had a musical automation band. It was 4 robot musicians floating in a boat, and it could program them by adjusting pegs on rotating cylinders. You could change what the robots played, move a peg, change a note, rearrange the pattern, compose a new song. Al-Jazari had invented the mechanical equivalent of a music sequencer, where the program was physical pins and the output was sound. He even documented the first systematic use of camshafts, converting rotary motion into linear action, the same principles that would drive the Industrial Revolution 500 years later. His manuscript survives in multiple copies, and the earliest at Istanbul's Topkapi Palace. You can see reconstructions at the Science Museum in London, where in 1976 they actually successfully rebuilt his scribe clock from his 800-year-old instructions, and it worked perfectly. Donald Hill, who translated Al-Jazari's work, wrote that it was impossible to overemphasize the importance of Al-Jazari's work in the history of engineering. Yet most people have never even heard his name. Now, let's move a little bit more forward to the philosophers and a few of the frauds, believe it or not. By the 18th century, Europe had caught up to where the Middle East had been 5 centuries earlier. But now automata came with philosophical implications. René Descartes had actually written in 1637 that animal bodies were machines which, having been made by the hands of God, are completely incomparable and better ordered than any things humans could build. He was talking about all the machine work there. But not only that, he imagined what would happen if machines could speak when touched, cry out when hurt, but he never believed that they could think. At least, not like humans did. But he even left us with a test to really be sure it was a robot and not a human, in case it ever became too hard to distinguish the difference. In his Discourse on the Method, book 4, around page 300, he outlined a Turing test that predates the Alan Turing's own Turing test, which I'll talk about here in a moment, by over 300 years. Again, he was thinking about talking thinking machines in the 1600s. We're still not to the 1900s yet. He specifically is quoted saying, "If there were machines bearing the image of our bodies and capable of imitating our actions as far as it is morally possible, there would still remain 2 most certain tests whereby to know that men, or that they were not men, not therefore really men. Of these, the first is that they could never use words or other signs arranged in such a manner as is competent to us in order to declare our thoughts to others. For we may easily conceive a machine to be so constructed that emits vocables, and even that emits some correspondent to the action upon it of external objects, which cause a change in its organs. For example, if touched in a particular place, it may demand that we wish to say it. If in another, it may cry out that it is hurt, and such like. But not that it should arrange them variously, so as appositely to reply what is said in its presence, as men of the lowest grade of intellect can do. Descartes, Discourse of the Method. Now, I could dive into that and go really heavy, but let's think about that for a moment. For the first part of his test, many AI models have actually passed that as of 2025. There's recent papers, which I will link in the description, show that our best language models have in fact fooled humans consistently enough to make us believe we're conversing with another person. The words are arranged appositely, the replies are contextual, the conversation often flows natural. Maybe not all the time, but often enough to pass. Even Descartes would have to concede that at this point, machines can now at least declare thoughts convincingly enough that we can't truly tell the difference. However, his second test cuts a little bit deeper into territory we still can't navigate perfectly, or at least agree on. He argued that machines would inevitably fail in certain others from which it could be discovered that they did not act from knowledge, but solely from the disposition of their organs. In other words, they'd be exposed as mechanisms, not minds. Yet here's the uncomfortable question Descartes didn't pursue. Are human actions fundamentally different? When we build, create, or respond, are we exercising some transcendent faculty, or are we just executing an incomprehensibly complex cascade of if-then statements written in neurons and chemistry? Our organs, our brains, our nervous system have dispositions too. The difference between us and machines might not be that we're not silicon and metal, but that we're mechanical in ways so intricate we can't even recognize our own programming. Unfortunately, this part of the conversation is out of the scope of what I'm talking about here. However, I explore what it is meant to think and deeper in a few articles, which, of course, I will link in the description. Descartes and his continuing this challenge of automation, we actually move forward in history to someone named Jacques de Vaucanson and his flute player of 1737, actually playing the flute. Real breath from leather bellows, real fingers covered in leather for pliability, covering real holes, a moving tongue controlling airflow. It knew 12 songs. Musicians complained that it played shrilly, but it still played. And his follow-up, the digesting duck, seemed even more miraculous. It ate grain, drank water, digested food in what Vascon would call a chemical laboratory, and defecated through the usual passage. However, the duck was a fraud. When magician Jean-Eugène Robert Houdin examined it in 1844, he discovered the trick. Pre-stored fake feces, green-dyed breadcrumbs, released while eaten grain collected in a separate compartment. Yet, even as a fraud, it advanced the conversation. Voltaire wrote, "Without the voice of Lamour and Vacan's duck, you would have nothing to remind you of the glory of France." The duck burned in a museum fire in Krakow around 1879, leaving only heart-warped wings in the ruins. The era's most sophisticated automata actually came from Pierre-Jacques Droz and his son. Their writer, completed in 1772, contains over 6,000 parts and remains programmable to today. You can still make it write any text up to 40 characters by adjusting a wheel where each character is selected individually. It dips its quill in ink, shakes its wrist to prevent dripping, and its eyes follow the text as it writes. At Switzerland Musée d'Art d'Histoire, on the first Sunday of each month, it is still writing these messages. Sometimes it even writes, "I think, therefore I am." Here was Descartes' test made mechanical, a machine arranging words, yet it wasn't thinking. It was following instructions encoded in wheels and cams. The question had fully shifted from can machines think to what's the difference between thinking and perfectly imitating thought? When patterns became programs. The answer came from an unexpected source, the textile industry. Joseph-Marie Jacquard's loom, patented in December 23, 1801, transformed weaving, but more importantly, it transformed the concept of instructions. Before Jacquard, complex patterns required a master weaver's consent. Before Jacquard, complex patterns required a master weaver's constant attention. Reading design and manually selecting threads, Jacquard's innovation was radical. The pattern became the program. Chains of punched pasteboard cards fed through the loom. Each card controlled one row of the pattern. Where there were holes, pins passed through to activate hooks and raised specific threads. Where there were no holes, the pins pressed against the card, leaving threads in place. The weaver just operated the loom. The cards contained the intelligence. By 1812, France had 11,000 of these looms. Patterns that once took months to weave now took days. The cost of complex textiles plummeted. Lien weavers rioted and attacked Jacquard, burning looms in fear of unemployment. The first tech backlash against automation. Sounds familiar, does it not? Then, from there, you have a man by the name of Charles Babbage, who saw these looms and recognized something profound, or at least usable. He created something called the difference engine, a project which unfortunately stalled in 1834, but he was convinced that he could make something more ambitious. And he started work on something called the analytical engine. Not just a calculator, but a general-purpose computer capable of any calculation that could be described. He adopted Jacquard's punch cards wholesale, but separated them into three types: operation cards, what to do; variable cards, what numbers to use; and number cards, data storage. The architecture he designed, a mill for processing, a store for memory, input devices, output devices, is exactly what sits on your desk today, just made of brass and steel instead of silicon. The machine was never built. The British government had already spent £17,000 on the failed difference engine, enough money to buy 22 steam locomotives. Babbage kept refining designs for 40 years rather than building, creating what Tim Robertson's 2021 analysis calls 120,000 words, describing 6 phases of evolution. But, luckily, the Science Museum in Britain decided it would have worked. They built his difference engine number 2 between 1985 and 1991 using only techniques available in Babbage's time. And fun fact, it calculates perfectly. What Babbage designed mechanically, a woman by the name of Ada Lovelace stood conceptually. In 1843, Ada was translating and annotating Luigi Menabera's article about the analytical engine, and she decided to add some notes, but not just any notes. Her notes were 3 times longer than the original writings. Especially her note G of these notes, it contained what everyone agrees was the first proper computer algorithms. A method for calculating Bernoulli numbers that demonstrated loops, conditional branching, and storage of immediate results. But more crucially, she saw what Babbage hadn't fully articulated. The analytical engine has no pretensions whatsoever to originate anything. It can do whatever we know in whatever order we choose to perform it. A. Lovelace. This became known as Lady Lovelace's objection, and it seemed pretty definitive, and the evidence showed that she was correct. Machines followed instructions. They couldn't create, they couldn't originate, couldn't think. They were, in her words, incapable of doing anything we didn't know how to order them to perform. For a century, this settled the matter, until Alan Turing pointed out a flaw in 1950. What if we ordered them to learn? Alan Turing's 1950s paper, Computing Machinery and Intelligence, didn't just propose this famous test that everyone talks about in AI called the Turing test. It systematically demolished 9 objections to machine intelligence. The 6th objection was Lady Lovelace's objection. Turing knew her statement well, quoted it directly, then observed something she couldn't have foreseen. The analytical engine has no pretensions to originate anything, only if the program machines to be predictable. What if we programmed machines to surprise us? He proposed teaching child machines rather than programming adult machines or adult intelligence directly. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one that simulates the child's? If they were then subject to an appropriate course of education, one would obtain the adult brain naturally. The machine would learn, making mistakes, adjusting, improving. Its eventual behavior would be something we enabled but didn't directly program. Origination through education rather than explicit instruction. But Turing understood something even deeper about the nature of computing itself. In 1947, he wrote, "If a machine is expected to be infallible, it cannot also be intelligent. There are several mathematical theorems which say almost exactly that." The quest for perfect determinism was the enemy of intelligence. Machines would need to guess, to be wrong, to work probabilistically just like humans. This insight becomes more profound when you realize that all our computers already work this way. We just pretend they don't. My computer engineers that are listening to what I'm about to say, bear with me, give me just a little bit of philosophical reach here. Your CPU doesn't execute instructions in order. It guesses what you're going to do next. Modern branch predictors achieve 95% accuracy on typical applications. These are the things that help CPUs decide where instructions should go, how those instructions are going to be handled. They use a rough neural network almost. The AMD Ryzen processors in your computer uses perceptron-based neural branch prediction to anticipate which code will most likely run. In 2018, a vulnerability exposed that virtually every modern CPU could be exploited specifically through these predictions. We built our entire digital infrastructure on machines that guess. Again, take a grain of salt here, but that's not the only guessing that goes on. Think about the cosmos. Your computer gets hit by cosmic radiation constantly. Again, this is important. It sounds like I'm going off on a tangent, but high-energy particles from distant supernova slam into Earth's atmosphere every second, creating a cascade of secondary particles. At ground level, 95% of the particles causing soft errors are actually neutrons. They penetrate your computer case, your chip packaging, and when one hits just right, the neutron is actually captured by your silicon nucleus, releasing an alpha particle, and it'll flip a bit. IBM calculated one error per 256 megabytes of RAM per month for a typical desktop. Google's 2009 study found 1 bit error per gigabyte of RAM per 1.8 hours in the worst cases. Seriously, your computer needing to be turned off and back on again because something stopped working could have actually been a solar flare millions of miles away. We've built an entire infrastructure of redundancy and error correction to pretend our computers are deterministic when they're actually under constant bombardment from the probabilistic world we live in. Other than being educational, you might be wondering why this history and this process and understanding matters. Every generation thinks they've invented thinking machines because every generation has added a new layer of abstraction. Heron's ropes and knots in Greek society abstracted human performance into mechanical action. Al-Jazari's cylinders abstracted musical knowledge into pin patterns. Jacquard's looms and his cards abstracted weaving patterns into programs. Babbage abstracted calculation into general computation. And Alan Turing abstracted learning into algorithms. And now, we've abstracted cognition into statistics, or rather, statistics into cognition. The mistake is thinking that these layers replace each other. They don't. They stack. Right now, as you read this, errors are flipping bits in your device memory. Error correction is fixing them. Your CPU is guessing what instructions come next. Assembly code is managing memory allocation. High-level languages are handling your browser. JavaScript is rendering this page, and if you ask an AI to summarize it, you'll add another layer. One that can parse meaning from symbols, extract patterns from text, and respond in natural language. Each layer seems impossible until it exists. Then we normalize it, forget the complexity beneath, and declare the next layer impossible. And that's the pattern that continues. We abstracted our own limitations into a system that could transcend them. When you don't understand this history, you're missing the pattern. You'll see ChatGPT as either a breakthrough or a waste of time instead of a continuation. You don't realize that when you're talking to math that runs on statistic, that runs on matrices, that runs on code, that runs on electrons, that tunnel probabilistically through silicon, that gets bombarded by cosmic rays, you don't see the stack of abstractions, each one seemingly impossible until it wasn't. The question has never been, can machines think? That's like asking if submarines swim. The question is, what patterns will we abstract next? What complexity will we compress into simplicity? What impossible thing will we make normal, then forget it was ever impossible? We've been building thinking machines for 2 millennia. We're just getting better at pretending they're not built on chaos, uncertainty, and approximation, the same foundation as human thought itself. Every generation thinks they've hit the ceiling because they can't see the next floor being built above them. What's impossible today that our children will find mundane tomorrow? What ceiling are we staring at that's actually just tomorrow's floor? The one thing that history teaches us about the limits of computing is that they're always closer than pessimists think and farther than optimists can imagine. And someone somewhere is already building a machine to transcend them. Everyone knows AI started in the 1950s. Everyone is wrong by about 2,000 years. And everyone who thinks we've reached the limit now is about to be wrong again. Thank you, everyone, and have a good day.